So a cosmologist is somebody who studies the universe sort of as a whole, or the fundamental physics of the universe. So I often explain it as the universe from the largest to the smallest scales from beginning to end. Anything to do with the bigger picture of how the universe works. So cosmologists study things like the Big Bang or the future of the universe. They study what the universe is made of, how it works physically, like what the laws are that govern the cosmos. And so I've worked in various areas around there. I've worked in the early universe and like what happened at the Big Bang, that kind of question. I work on dark matter, which is one of the most important components of the universe, but we don't know what it is. And I've also thought a lot about the end of the universe and just various aspects of like, how does it work? What's really going on? I've been very fortunate in my career that I've had a lot of freedom to study what I'm interested in and to just kind of follow my curiosity. So I've had research fellowships where I'm not tied to a particular project, but I get to present, here's what I want to work on, and then I work on that thing. So I've just kind of looked at like what's the interesting question, where can I be really creative about this. So things like, talking to the theorists about what the new sort of physical model is they're thinking about, like what's the big theory that everybody's excited about, and then talking to the observers about the new telescopes that they're going to build, like what is this new telescope going to see about the first galaxies in the universe, and then trying to find ways to bring those together, trying to find out what can those telescopes tell us about those theories, and what kinds of experiments do we need to test those theories, and that kind of intermediate stage where you get to learn about every aspect of these questions and try and find new creative ways to bring them together. So that's kind of the area I like to work in. But in terms of topic, it's anything from black holes to early galaxies to cosmic strings to dark matter to microscopic black holes that might have started in the early universe, all kinds of stuff like that, because there's some interesting creative way I can approach the question. So we know that most of the matter in the universe, most of the stuff that has mass in the universe is totally invisible. We can't see it with ordinary light. It doesn't seem to reflect or emit light or absorb light. So it's hard to look at directly, but we can see that it's there based on how it affects things that are lit up in the universe, stars and galaxies. Like about a third of a proton mass per cubic centimeter is roughly how much dark matter is around here, and it's passing right through us. That's most likely sort of where we're at with dark matter. There's a lot of uncertainties. But yeah, so we're pretty sure dark matter is there. It seems to be important to the functioning of matter in the universe, to the growth of galaxies, to the formation of structure on the largest scales. But we don't know what it is, and there's a hope that maybe if dark matter particles, if they really are particles, probably they are, if dark matter particles collide in just the right way, they might annihilate with each other and create regular particles like things like positrons and electrons or quark pairs or something like that. And if that's the case, then regions of really dense dark matter should glow with high energy particles that we can see, just to some tiny degree. A lot of people have followed that possibility and looked for evidence of dark matter annihilating in the center of the galaxy or in small galaxies nearby or various places like that. One thing that I've been interested in recently is, what if that does happen? How would it have affected the first galaxies in the universe? So these clumps of dark matter where the first gas got together and formed stars and galaxies, how would those structures be affected by a little bit of energy coming out of the centers of these dark matter clumps? And then furthermore, if that is happening, how does that, or if that did happen in the past, how does that change what we can see with radio telescopes and with infrared telescopes, things that can look at those first galaxies? So, as far as we can tell, dark matter was part of the sort of primordial soup of the very, very early universe, and it was crucial to building up the first matter structures in the universe, the first galaxies, the first stars. It helped bring all that gas together and to allow it to form those first stars and galaxies. We have a reasonably good idea of the fact that, like, if dark matter were not there, then the gas that makes up our own galaxy, the Milky Way, would not have been able to come together enough to form the Milky Way as we see it today. So it's been a factor in the evolution of structure since the beginning. Whether or not it's been injecting high energy particles and photons, energy into these clumps, we don't know. And so that's what I'm trying to figure out, trying to model like what that would look like, how it would affect those first stars and galaxies, what you would see with space telescopes, what you see with radio telescopes that can sort of probe the neutral hydrogen that formed the first stars and galaxies at very, very early times. So in terms of how it affects, like, just it played a role gravitationally, how it brought matter together, the way you learn that is from modeling the gravitational growth of structure. So you do computer models to simulate matter coming together, and you see what happens if that matter coming together has pressure and like acts like gas where it can kind of puff up again, or if it's dark matter where it just has gravity and doesn't have pressure, it doesn't puff up. When you, like, if you let dark matter sort of fall toward itself, it's not going to bounce off, and it's not going to like kind of heat up the way that gas, if it falls together, it kind of gets puffy. So you have different dynamics around how things grow through gravity, if it's dark matter or if it's regular matter. And so computer modeling is a big part of figuring out how dark matter affected the gravitational sort of development of these structures. In terms of how we'll know if it's annihilating or not, that's a different question. And that's also something where you have to do computer modeling to see where that energy goes within that dark matter structure, where it goes when it goes into the gas, and how that changes the physics of that gas, and how it changes, like, maybe what it does is it blows out all the gas in the smallest little clumps of dark matter, and so you can only form galaxies in larger clumps of dark matter, and that would be something you would be able to tell the difference in a sort of large survey with telescopes. I think that what we really want is a big picture of the whole evolution of the universe and the structure of the universe. And so the beginning is part of that question, how did the universe begin? If you have a theory for the beginning of the universe, it generally has an implication for the end as well. And if you have the early universe and what was present in the early universe and how all the pieces fit together then and how it's evolved over time, then we can extrapolate into the future what dark energy will do and how it may or may not destroy the universe. As far as we can tell, all it does is make the universe expand faster. It doesn't seem to interact with anything else in any other way. It stretches space, and that's it. So all you can really study with dark energy, as we understand it, is you can study the evolution of the expansion of the universe, how it's changed over time in expansion rate and so on. And you can study the evolution, the sort of growth of structure in the universe. So how galaxy clusters come together. And you can do that by looking at the past and seeing, watching kind of that growth happen. And that's kind of it. Like there are some theories about dark energy that involve things that could interact with experiments. And so people are really hoping to find some connection with an experiment with dark energy, but it might just be a sort of aspect of the universe that there's some number that designates how this expansion works, and it's just part of how, it's just written into the equations of gravity. In my various studies in cosmology, I've frequently come across papers or talks that are about different ways the universe might end, and I'm always just fascinated by that question. And I notice that when I give public talks, the audience gets really excited about the question of the end. And I realize that it's just not out there in the public consciousness enough. Like, how do we think the universe is going to end? What are the possibilities? And it seemed like a fun opportunity to dig down on those and present like what we really know about the future of the universe now. What are the different possibilities? How are we distinguishing between them? While also talking about this sort of big scary destruction. And so it's not an immediate fear, and yet it's so overwhelmingly huge that you kind of have to laugh, because like, what else are you going to do? Like the whole universe is going to be destroyed. Like, okay. In practice, like based on what we think we understand, the timeline for that actually to occur is like 10 to the power of 100 years from now. Like, we don't know because it's a hard calculation and there's still a lot we're trying to figure out. I mean, we don't even know if the theory that suggests the possibility of vacuum decay is valid, right? It's the standard model of particle physics, which is this theory of particle physics that we've validated with experiment, but we know has some holes in it. Maybe vacuum decay will happen. Maybe it'll happen in 5 minutes. Probably not. Every time I talk about vacuum decay, I have to be really, really careful to say, please do not worry about this. But like, you wouldn't even notice it if it happened because it would happen so quickly, or like in a sort of bubble of doom that expands the speed of light, and so it doesn't matter. Like, you can't see it coming, and it just destroys everything immediately. Nothing you can do about it. You wouldn't see it coming. Nothing would be left. You wouldn't notice it. And it's all, as I said, based on these ideas about the standard model of particle physics, that where we know that there are missing pieces to that theory. And so we don't know which pieces may or may not come into play in real possibility of vacuum decay. And there are much more immediate things that we should worry about. I think the most likely scenario, as far as what we know about the universe now, is something called the heat death, which is where the universe basically kind of fizzles out. So we know the universe is currently expanding. We know it's accelerating in its expansion, and what's happening is really that galaxies are getting farther apart from each other. Everything is getting more and more isolated. And so if we follow that, extrapolate that into the future, in 100 billion years, every galaxy will be kind of on its own, unable to see other galaxies. In 100 billion years, if you put the Hubble Space Telescope up, it won't see anything. Most of them will have died by then, but some will be around, and that's it. All the other galaxies will be so far away from us, moving so quickly, we won't be able to see their light anymore. Anyway, in the future, like in 100 billion years, astronomers, physicists will have no evidence that other galaxies exist. They'll have no evidence of the Big Bang because they won't have any direct data about that. The sun only has about 5 billion years more of burning hydrogen. And even before that, in only about 1 billion years or so, it'll get so hot or so bright, and it'll expand a little bit, and it'll boil off the oceans of the Earth, and the Earth will become uninhabitable. So maybe we'll live somewhere else. I don't know. But humans will not be on Earth. Well, so if we're assuming that the heat death is where we're headed, where after you stop being able to see other galaxies, then the universe continues to expand, and stars burn out in our galaxy, and matter decays, and you end up with black holes, and the black holes evaporate, and then you're just like sort of like this cold, dark, empty universe. If that's where we're headed, then on the time scale, we're at the very beginning, because the amount of time that takes to get to that end stage is like you putting exponents on exponents on exponents. Like it's really, they're not good words for the number of years. But if you judge by like how much has happened, we're almost at the end. And it depends on a lot of things. And one of the things it depends on is how often galaxies are colliding with each other and like coming in to mix their gas and form new stars that way, right? And so as the universe is expanding, galaxy collisions are happening less often, and starbursts are happening less often. And so we can look back and we can say, somewhere 6 or 7 or 8 or 9 billion years ago, there was way more star formation, and it's been declining. And you can work out that of all the stars that ever formed in the past, or that ever will form in the future based on our evolution, about 90% have already happened.